In this video, we are going to be looking at the equilibrium constant Kc. Now, so far we have looked at reactions that are in dynamic equilibrium. So, for example, the Haber process is one that we have looked at. And as we know, this process is in dynamic equilibrium, means that there's a forward reaction and a backwards reaction. And that we know that equilibrium has been reached once the concentrations stay constant, okay? And then we also looked at factors that we can change that can shift that position of equilibrium, okay? Whether the position of equilibrium lies more towards the products, which means we're creating more products, or whether it lies more towards the reactants, which means we're going to have more reactants, okay? So we looked at pressure, concentration and temperature shifting that position of equilibrium, okay? As you remember, catalysts don't shift the position of equilibrium because the forward rate and the reverse rate are increased by the same amount, okay? So the position of equilibrium is only affected by pressure, temperature and concentration, okay? The importance of the equilibrium constant is it essentially tells us where that position of equilibrium lies, okay? So the constant tells us where that position of equilibrium lies. It allows us to quantify the position of equilibrium, okay? Now, when it comes to the equilibrium constant Kc, we need to look at how we might write an expression for Kc, okay? And that's specific to the reaction. So I'm just going to do a general reaction here. I'm literally just going to use the letters for it. So the Kc expression can be written for anything that is in dynamic equilibrium. Okay, so essentially we've got reactants A and B forming products C and D. The lowercase letters are essentially the balancing numbers. Okay, you need to know that the Kc expression can be written for this equation over here and for any equation that's in equilibrium. We do the products at the top, so it's the concentration of each product. So concentration we show by using square brackets, okay? Don't use normal brackets, it's square brackets. And we raise it to the power of the balancing number, okay? So that's lowercase c at the top, and then we multiply it by the concentration of the other product raised to its balancing number, okay? And then we divide all of that, and the reactants always go at the bottom. So now we're going to do reactants here. So it's the concentration of A raised to the balancing number multiplied by the concentration of B raised to its balancing number, okay? And that is how you are always going to write out your Kc expression. So essentially it's the concentration of the products, each raised to their power, their balancing number, divided by the concentration of the reactants, each raised to their balancing number, okay? Let's now actually apply this to an actual reaction. So let's just go for the Haber process again. So you always write out the balanced equation first. Okay, so the Kc expression for this is going to be the concentration of the product, so that's just ammonia, raised to its balancing number. So this is going to be squared divided by concentration of nitrogen. Now, because there's no balancing number in front of there, that's just a 1. So that means this is raised to the power 1, which means it's just itself, multiplied by the concentration of H2, and the balancing number for that is 3. So it's to the power 3. So that is the Kc expression for the Haber process. And you should therefore be able to do this for any reaction that is in dynamic equilibrium, okay? You also need to know how to calculate the units for Kc. Given that we're talking about concentration of things, units for concentration are moles per decimeter cubed. So I'm just going to do this in red. So at the top, we've got the concentration of ammonia, so moles per decimeter cubed, but that is all squared. So I'm going to square that. And it is divided by the concentration of nitrogen. So again, that's moles per decimeter cubed, and multiplying that by the concentration of hydrogen raised to the power of 3. So this is now moles dm minus 3 raised to the power of 3. Okay, if you then simplify that, so if I just simplify this bottom part, so 1 lot of that times by 3 lot of that, 1 lot of this multiplied by 1 raised to the power of 3, so I can simplify that to 4. So that means this bottom part here raised to the power of 4. And if you remember the rules of indices, if you're dividing them, you do 2 minus 4, and that's going to give you minus 2. So if I now rub this out, so there's a little bit of maths here. So it's going to be moles dm cubed raised to the power minus 2. And then if you just expand the bracket, it becomes moles minus 2, and then minus 3 times minus 2 becomes dm to the power of 6. Okay, so this is the way to work out the units, and again it's going to be specific to the reaction that you do, so you should be comfortable simplifying expressions with moles per decimeter cubed raised to different powers. Okay, so this, for the Kc expression of ammonia, not ammonia, the Haber process, these are the units for Kc. Okay, another thing that is important to note is the value that we get for Kc and what it tells us. Okay, now it's also worth noting, so when I've mentioned concentration of these, it has to be the equilibrium concentration. Okay, so the concentration at equilibrium is what you should use here. If they give you the equilibrium concentrations, all you do is you plug it into this Kc expression, and you should get a value from that. Okay, so that would be your Kc value. These would be your units for this specific expression over here. If you have a Kc value that is exactly 1, okay, that tells you that the position of equilibrium is right in between, or right in the middle. Okay, so the position of equilibrium is in the middle. If we have a Kc value that is smaller than 1, okay, that tells us that the position of equilibrium lies towards the reactants. And if we have a Kc value that is bigger than 1, I don't know why I used equal signs, but if we have a Kc value that is bigger than 1, that tells us that the position of equilibrium lies towards the products. Okay, so the significance of Kc is quite important because it tells us where the position of equilibrium lies.